So today I'm just going to paint 6 brief vignettes about AI for astronomy as a science and AI for astronomers, us as a community. Let's get right into it. I've got a table of contents here and there's a lot to go through. Of course, you can read each of these subheadings here, but I really want to thank the folks who made this possible, and especially the early career researchers who are on that first row here. You can see that this is a collaboration between at least these organizations, but also with input from many more. And again, you're actually going to hear hopefully in the latter half of the hour from Joe Chuka, who is also one of our great collaborators here. So many thanks to them for enabling all this. And I want to get started with this idea of how do astronomers trust or build trust in AI for their research tasks. You might have had conversations kind of like this one, where somebody says, oh, AI is so great. It's really useful for me for coding. And then somebody else says, I used it for coding, but it was terrible. I'm never going to use this again. And it's kind of curious that the same benchmarks are giving rise to these discrepant realities. And this is especially true back in 2023 and early 2024, where we sought out to evaluate how do astronomers use AI in their research, and how can they use it effectively? How do they learn to use it effectively? And so we built this out in a Slack workspace, the Space Telescope Slack workspace, which has 1,000 users, of which 200 identify as researchers. Basically, all of them have PhDs in physics or astronomy. And so I built this LLM-powered, or really retrieval augmented generation-powered Slack bot, where a user can query this bot and ask the question like, what's the origin of multiple stellar populations in globular clusters? And then the bot will go and retrieve from a corpus of 400,000 archive papers from the astronomy literature, find ones that are relevant, and synthesize an answer, perhaps with citations like this one. And so this is a real data point from our study. And you can see that it's giving an answer in about 150 words or so, with 3 real working links that users can then go and validate and see if these are supporting the right claims. We also allowed users to give ratings, thumbs up or thumbs down emoji voting. Just makes it easy for people to leave a data trail that we can then go and analyze. And we also did this in a group environment. So this is actually in a private channel because users had to opt in. We actually got an IRB approval for this, and then had users basically allow us to use their anonymized interactions, or at least somewhat the pseudo-anonymized interactions, where people can chat and learn from how others are using the tool, in hopes of understanding how that group environment might also build trust. As you can see, these are this is the actual conversation that happened. People are like, yeah, this is an okay answer for this reason. All right, we found that over the course of 4 weeks that we ran this study, very time-capped, obviously astronomers are initially trying to get feelers for how does this bot work. But they did ask very diverse types of questions. We had about 40 participants and 368 queries over the 4-week study. And we then received, we looked at all the queries, questions like, what's the origin of multiple stellar populations in globular clusters? And without having a preconceived category scheme for coding these questions, and that is categorizing them, we inductively coded these, or really I should say 3 members of the team spent a lot of time deliberating and coming up with ways to code these until they reached consensus about what the categories were. We then performed semi-structured interviews with 11 participants. And so here is the coding scheme. You can see there's several types of categories here, ranging from knowledge-seeking questions to bibliometric search questions, which the Slack bot was not equipped to do. It did not know anything about the metadata, like the number of citations, and then or author list or any of that. And then it was given. Then we could look at the results, which can be distilled into the net number of thumbs up and net number of thumbs down, or percentage of those. And so as you can see, there's types of questions that people ask, ranging from specific factual knowledge-seeking questions to deep knowledge question to stress testing and trying to understand what the bot's capabilities were at the time, or looking for specific findings in authors. Okay, this actually summarizes the entire data set that we have, almost all of it, in fact, where we're showing each user as a row and each of their queries coded by this inductive coding scheme. You can see here, same as before, and the sequence number. And there's a lot of stuff going on here, but one of the takeaways I want to impart is that people ask a lot of different types of questions, and they often started off trying to understand some specific factual questions. If you look at the kind of pinkish colors, you'll see that many of the users tended towards asking those questions up front. And we think this is because they were trying to develop a sense of, how do I trust this? In fact, they usually have the answer to that specific factual question, and they want to know, did this work according to my intuitions? How can I trust this? Do I know if it's giving me an answer that I think I already know in my head? And what we find indeed is that then they progress to other types of questions here. You can again see the net thumbs up versus thumbs down in terms of how well did not just the person who asked the query, but also the entire group community, what the net result was. And the last thing I want to say too is you'll notice some of these are hollow markers, they're not shaded. That's when users rephrased their query from before in different words. We noticed that was another thing. People thought maybe my wording, my prompting wasn't good enough, and so they try to repeat their query. All right, there's a lot of things to take away here. One of the main points that we want to impart was it's really important to know how users can evaluate queries, and so we decompose these queries into 5 different criteria that we discuss at length in this column paper. Definitely go check that out if you're interested. And how that maps onto the query types that we from our inductive coding scheme. And then finally, the kinds of metrics that we might want to use to actually design these kinds of evaluation studies in the future. So there are different ways that you might think, maybe you prioritize certain types of evaluations. And so we, posit some methods or metrics that you might use to study this. I don't want to harp on this point, but we did notice that LLM responses to younger users' queries happen to be rated more positively. There's a similar trend if you looked at years since PhD. And it's noisy. We didn't want, again, this was an appendix because we didn't want to get too much into this, but it was quite interesting. I have some hypotheses about why this is, but it did tend to be that the younger users got more thumbs up from, again, the community, not just from themselves. Okay. So with that, I'd just like to say, check out the paper. Within that QR code link, there's also links to the data sets on Hugging Face, which contains the full anonymized query data and also a set of representative actual astronomy eval questions. All right, let's keep going. Navigating the cosmic library. So if you're interested in astronomy bibliography or really any type of finding papers, you might ask, how do you even get started? One way is just saying, I think I know an author who works in this field. I like their papers, let me go look them up. Or maybe even you go directly to the journal or the conference proceedings. And you say, I trust NeurIPS, so I'm going to go look at all theirs. Another way to do this is through keywords. Oftentimes in astronomy, people are required to tag their papers according to certain keywords, such as through something called the Unified Astronomy Thesaurus. You might ask your friends or your professional network, like my PhD supervisor surely knows the literature, so let me go ask about the canonical papers. Or maybe you go to a conference or you hear a visiting speaker talk about some papers, and you're like, I guess I'll go look that one up. You can look through citation graphs, things like Semantic Scholar and stuff, do a good job of this, and then, or ADS as well. And then semantic search, which is really what I want to talk about. Understanding the semantic content within the text itself. And in order to get there, you need to somehow turn some piece of text, like let's say a paper abstract or maybe the full body text, into a text embedding, that is a vector representation of that text. And in order to do that, it's facilitated by some sort of language model, usually not like an autoregressive language model that's predicting new tokens, but rather it's putting out an embedding vector or a text embedding. And the nice fact about having 2 sets of papers is it's kind of hard to do search or measure similarity between them. But if you send them into this abstract space, then you can now look at something like a cosine similarity between those two and decide, okay, these two are more similar than some third paper. Okay, so what we do then is grab at the time 400,000 papers, actually just the abstracts for now. We turn those into text embeddings using the GPT-3 model at the time. And that's 1536 dimensional. And then we distill that down into 2 dimensions through UMAP, the uniform manifold projection. And so you can see this is kind of the 2D UMAP space as a heat map here of the entire astronomy literature. This is something that Kartik Iyer really pushed forward on. And I'm sorry that these are really small little tags there, but it's no matter. Kartik went to a nice diffusion model and turn this into like a D&D style map of the lands of astronomy papers. And then, you can definitely tell what the clustering of papers are showing there, but this makes it a little more clear. And just zooming in, you can actually kind of see like what's going on here, where some of the very established research areas are kind of these like peaks in the distribution, these mountains, of galaxy formation, evolution, or star formation, topics that have been, captivating astronomers' attention for a while. And newly emergent research areas are kind of these shallow waters here, where land is just emerging, and even still, you're seeing topics such as pulsars or this multi-messenger astronomy, which is definitely a newer field. Some of the others. So beautiful paper. I want to kind of talk about what we can actually do with this. One specific thing is we can look at how our Unified Astronomy Thesaurus, UAT, and with some of them sort of hierarchically clustered into different subfields of astronomy, how do they span this space? Do they make a complete spanning of the space? And that's actually quite interesting. There are some areas where maybe you can see, there are some areas where maybe these are missing, and we could come up with new keywords that describe a lot of the literature. Another interesting thing we can do is look at how observing facilities cover this map. This is also really nice because you want to know things like, where are all the Hubble or JWST papers going? What is the Hubble telescope doing? In terms of this space. And so you can look at this mapping of how these observatories are landing in the literature. You can even compare this with the time evolution of the literature and seeing how observatories give rise to entire new subfields. Another interesting thing to do, just mentioning, is that you can also see some of these missions if they're designed for very specific research topics, but then you can see that, for example, Kepler here had an extended phase of its mission, called K2, which enabled a whole new field in planetary science, or exoplanets, that maybe it wasn't initially designed to do. And so this is another example of how you can measure the impact of different telescopes. And in fact, that's what I want to talk about now, which is what is the scientific impact of our telescopes? So if you look at this plot, it's a little inverted. You'll see why in a second. If you look at the number of publications per year from Hubble, you can see that this started off in around 1990, and has up till 2025 or so risen to something like almost 400, 300 or so guest observer proposals, papers. So these are papers where somebody proposed for a specific set of observations. Could be a survey, could just be a single pointing, and then they wrote a paper about it. And so that's counting those papers. You can see the same in the shaded, the denser shaded region here with JWST, which launched, just in 2022, I guess is when they began science operations, and has rapidly been scientifically productive. But this is just the guest observer papers. If you look at the archival impact of the science, you will see that it's actually very large. This has continued to grow, and even for JWST, such a new mission, is already becoming very scientifically productive. This matters to us at Space Telescope a lot because we maintain the Mikulski archive for space telescopes, and we really want to ensure that this democratizes science. And we would love to know how many papers per year do these archival, do our archives enable, amongst the research community. But somebody needs to go out and read the entire astronomy literature to understand which of these use HST or JWST papers or any NASA mission. Now, of course, if the authors are good, they will, follow all of our instructions and create the digital object identifiers as we have requested, but often this is not the case. In fact, one of the things I advise on is a project where we are trying to ensure compliance with DOIs for JWST data, and it is not 100% compliant. But we are trying to enable a way to make to let NASA know what the scientific impact of its investment in observatories is. So just to spell it out, the main question here is, given a paper's text, can we label, is it a HST paper? Is it a JWST paper? Is it going to be a Roman paper, which is going to launch later this year? Is it a passing mention, or is it a science paper, right? Does it do new science with this data? Or maybe is it a calibration program that enables new, some engineering project comes up with a new mode of observation. And also, since we want to build trust in this, we want to know how confident is this classification. Maybe ask it to provide justification as well, and also extract quotes that supplement its reasoning. And so an example of this in action, so this is in one of our real systems, is we'll take all of the text in the paper. So we take the title, the abstract, and body text, concatenate that, or convert this to Markdown and concatenate it. And then the first thing we want to do is take a first filter through the full text and distill it down to a couple of mission-specific keywords. So we do keyword expansion, where we then look at all the relevant keywords and make sure that we're not just reading 20,000 tokens, but rather we're focusing on, say, the 2,000 tokens in shorter snippets that matter the most. And importantly, this allows us to re-rank those snippets according to the relevance of our task at hand, which is to fully understand, is this a science paper? And oftentimes you'll see things like, hey, this, we in the future, we will want to, conduct a JWST survey in order to verify, these theoretical results. That would, be removed by the re-ranker step, and that requires its own LLM. You can then try to get structured extraction of the relevant quotes and a reasoning chain for the direction that the LLM is headed. And then finally, just to make a final prediction and classification with a score. Each of these steps was actually kind of battle tested. We built up a golden sample and thoroughly evaluated it, which is why we landed on this very specific, process. But initially, the system design looked quite different. So I just want to say it's really important, as we all know, to look at your data. It's really important to thoroughly evaluate it on a held out golden sample that you really trust. Again, this was something that took a ton of FTE because we had to have 5 or 6 staff go and look at the same data set again and again and again until they converged on an answer that yes, this is indeed a science paper, not some fringe mention. Okay. This is now being used in operations at Space Telescope. But the code is public, and in fact, we also submitted the code or a short modification of the code to an open Kaggle data challenge, which placed near the top of the leaderboard. It was like number 3 in this leaderboard for again doing telescope bibliographies. So you can go and take a look at that. You can play with the code itself, and maybe even use it. Okay, I kind of want to switch gears a little bit, and now focus on the latent space. Like, what is happening in terms of the mechanisms of the neural networks that are parsing, the text data and converting them into some sort of embeddings. How might we interpret the features that exist in this embedding space? So again, this is a beautiful map by Kartik Iyer's Pathfinder paper. And one of the reasons why we can't just read a feature off of a single neuron activation is because of these two effects known as polysemanticity and superposition. They're kind of related effects. So with polysemanticity, the issue is that a single neuron, so I'm representing this bar or whatever chart of heights there as your embedding vector. You might look at a single neuron activation, but you'll find that it has multiple semantic meanings. And likewise, if you look at, you think of a semantic feature and you're like, oh, here's a concept I want to look for, you'll find that it's spread across multiple neurons. And this makes it really hard. It's not one-to-one mapping, but it's a many-to-many mapping of neuron activations and semantic concepts. So what we can do is use a sparse autoencoder to take the dense embeddings and train a very simple neural network. It's really just a deep projection matrix, a nonlinearity, and then we basically get some latent space. That latent space in here now, this sparse autoencoder latent space, or SAE latents, those can then be, you can then remove all but the top K of them so that they're extremely sparse, and then have that deep projected back down into this reconstruction of the input. So again, these are the embeddings here, but we also have some SAE features that arise. And we produced an auto interpretation pipeline. I'm not going to go through all this, but all this is to say that if you look at the decoder, it really it's just a projection matrix, and each column vector in there can be interpreted as the activations of a particular feature. So you can look at each of those columns and say which bits of text is this activating highly on? And the ones that it's most highly activating on, you should say, is there a common theme that they're all highly activating on them? And so we built this, so maybe all the activations that are high are about arithmetic operations and transformers, and all the non-activations, there's no common theme. It's just a bunch of who knows what. And then, we can sort of verify this in our auto-interpret pipeline and try to understand how confident we are about auto-interpreting the features or labeling them. One thing that arose in this, which is quite interesting, I want to harp on the point that we are using the dense embedding spaces, right, of an embedding model. We are not using something like, like an LLM at the token level. So in this case, what we're doing is we're taking the entire parcel text, right, like an entire paper abstract, and trying to distill it into a dense embedding vector and then tease out the sparse activations from that, the sparse features. And that's different than looking at like a token by token activation as you progress through, some piece of text. Okay. What we find, interestingly, is like the emergence of these feature families. There are these block diagonal structures which are actually hierarchical in nature. And so when we look through the AstroPH literature, these are just 5 sort of feature families, as we call it, where there's a large parent feature, something like black holes, but then within it, there's actually co-activation. So activation at the same time, correlated activations of other features that are oftentimes subsets of that topic. Something maybe like accretion onto black holes, or maybe an merging of black holes, or something like that. And so what we see is that in the structure that there is this co-firing of these features in SAEs of a given model size. And then if you look at this is another example of a specific one. This is now in the cs.lg, the machine learning archive listings. And what we find there is that, in optimization techniques, there's this whole family of other features there. Another thing that we found is that by using the SAE, again, as I said, they're the projection matrix in the decoder of the sparse autoencoder, that gives you these, that matrix can be steered. Like you can actually change the activations based on a feature that you think you understand. So what you can do is, if you're trying to look for a query which is focused on a specific topic, you can actually identify, if you've identified a feature that's relevant to it, you can simply just upweight that feature. And what we found is that this represents a Pareto improvement of rewriting the query compared to just taking that original query and then taking an LLM and say, rewrite it so that it's more, more about X topic. So you can look in the paper if you want to hear more details about that as well. But this was another interesting finding. Okay, parallel front. These hidden mechanisms, we also want to take a look in vision models for astronomy. So yesterday, I gave a talk where we looked at how data can be passed into a vision model. It lands in some embedding or some latent space, and that can be used for some downstream prediction. But in many cases, these foundation models can also be decomposed into interesting sparse features. So this is exactly the same playbook that I just mentioned. We've got our case sparse autoencoder, and we can look at what these activations are doing, and we need to come up with an interpretation pipeline for them. And one of the things we do, I teamed up with Mike Walmsley, who was formerly in the Galaxy Zoo team and has now departed for industry, was to look at the ZooBot. This is the citizen science classification, a classification algorithm for supervised learning. So up there is what ZooBot, basically predicting whether galaxies are spirals or barred spirals or three-arm spirals. It's like that kind. It learns those kinds of topics. And then we can look at how the latent space might decompose into interpretable features. So I'm just listing some of the top sparse autoencoder learned features. So these are discovered features from these the supervised foundation model. And then we also trained a masked autoencoder, which is a nice scalable self-supervised foundation model. This is all on Euclid imaging, by the way. I should have mentioned that earlier. Euclid is like a European Space Agency telescope, which is doing space-based imaging. And we've got millions of galaxies in here. And you can see the kinds of features that are being found just, again, on their own by this sparse autoencoder framework. And we can see, how well do these align with existing concepts that we know well. And so if you compare against something like a PCA decomposition, it's able to identify some some large trends which have, high Spearman correlation with galaxy zoo classes. These are things like, is this a disk galaxy, or is this a, not disk, or is it like a like more of a cigar shape or something like that. But the sparse autoencoder actually just has a distribution towards more heavily aligned, with galaxy zoo features overall. So we do find that they are more interpretable, but we can also do the same thing in a supervised learning task. So if you take your data and you want to go and make some prediction through the vision model, you can actually impose the sparsity constraint end-to-end during training. So in this case, we might be predicting something like, let's go and try to measure these emission line strengths, which can be used to basically compare or designate which of these are star-forming galaxies from active galactic nuclei. And it turns out that if you make them very, very sparse and try to train it to do this kind of task, you end up with coherent and highly interpretable features. And so these are just 4 features that were found in a case sparse. This is what I call sparse feature network, because again, it's a supervised task, but we are imposing the sparsity constraint in a way to make them hopefully more interpretable. So this turns out to have like low mass kind of dwarf galaxies are over in that feature on the upper left. You've got sort of what are called liner galaxies or on the AGN side of things. These look like older stellar populations, but may also host accretion onto supermassive black hole. We actually find extreme emission line galaxies in the lower left. This is a very rare population that we did not expect to find. But this sort of autonomously was able to identify these. And when we followed some of these up, we realized that these had really, really interesting spectra. And then finally, these like diffuse objects, which also kind of span this like low ionization side of the star forming cluster of galaxies here. Okay, and the last bit with my negative 2 minutes left is the Platonic representation hypothesis. I'm just going to kind of give the teaser for this. The Platonic representation hypothesis says this: as neural networks get deeper, even across modalities, they might converge towards some shared representation. This is something that was put out in a position paper by Fiu et al. And so you might say that some image of this cone next to a red sphere is similar in its embedding space representation as the text version of that. And there's some data to justify this. And so we ask the same question, that the Platonic representation hypothesis, if it's true that the alignment of the embeddings should increase with scale, even across modalities, is that true in astronomy? The short answer is we do this across imaging and spectra. We look at Astro foundation models and ImageNet trained foundation models, and we find indeed that there is convergence. There's a lot of caveats, a lot of details in this paper. This was a spotlight in the recent Machine Learning for Physical Sciences workshop, but you can take a look at the archive paper link there. So let me just leave up all the things I talked about today and give a thanks to my collaborators here once more. Thanks for listening.